All right, welcome everybody. This is Fred Schenkelberg, and welcome to today's Accendo Reliability webinar. Um, this is a follow-on from what I did last month, where we had a I had received a good number of questions concerning accelerated life testing. And Bill, for your edification or to avoid any confusion with anybody, this is quantitative, if I get that right, where we're trying to essentially figure out a time to failure distribution, or will this thing last long enough to some criteria. Those kinds of are flavors of testing that we do, sometimes called life testing, or durability, or there's a whole bunch of other names for it, but I typically use accelerated life testing. And so I didn't quite finish all of those questions last time, and considering doing another session just to finish out those questions. And I'll extend the invitation here. If you've got questions, or if questions come up in this webinar, we can talk about them here for sure. Also, just send them over. Send me an email or a voicemail, and I'll try to get you an answer as quick as I can, or get you some meaningful information, and we'll add it to the list for the next webinar on questions about ALT that you may have. So we'll see what we get with that. So today I want to talk about, well, partly how did I learn accelerated testing, and maybe provide a model or incentive or a prod to you to learn ALT. Now, a lot of what I'll be talking about applies to learning pretty much anything, yet we'll use ALT as a vehicle for that. And maybe it's, part of asking for questions about accelerated testing and working with clients over the years on it is I've had the opportunity to learn quite a bit about it. By no means an expert in all aspects of accelerated testing, yet have enjoyed the entire process. And in that process, let me see if I get my cursor to go here, I've produced a few good ALTs. And I heard it years and years ago that a presenter at a conference was rattling along and paused to see if there was any questions. And somebody asked the question and says, well, that is a good question. And said, a good question is defined as both it's insightful and I happen to have an answer for that, right? And so I could talk about that. That's a good question in that person's opinion. The same goes with accelerated life testing. You can have a good accelerated test. It actually produces results, information that is both understandable and useful. Somebody needs that information to make a decision. And I would call that a good accelerated life test. It actually serves a purpose and adds value to your organization. It's all good. Sometimes, though, we create pretty bad accelerated tests, and I've run into a handful of those over the years. Just a couple months ago, somebody asked for some help considering how to run an accelerated test for a batch of products that they were suspicious that this particular failure mechanism they were concerned about was more prevalent due to some manufacturing errors. And they wanted to make sure. So they were going to take a subset of those units and see if they exhibited that failure mechanism or not. And they needed to accelerate it, because normally it would take a long time for it to occur, yet much less time than they needed the product to actually work for. So it was one of those dilemmas. Then they modified the test and then came back to me to ask for my data analysis of it. They had very few samples. They had on the order of 20 samples, and they started accelerating them. And the test was designed such that that accelerant would give them the duration, the simulated duration of experience for that product for, I don't know, it was like 10 years or something like that. And what they decided to do was take 2 of those samples out of the test equivalently of like every year and tear it down to see where it was. And I asked, why are you doing that? Because at the end of this test, you're going to have only 2 samples that have actually exhibited that they operate for the minimum duration that you want to experience. And at that point, the results are kind of not all that valuable. And what are you expecting to learn from the teardown? And they said, well, we really want to know if anything else is going wrong too. So we're going to tear it down and see what else is going on. And it's just kind of, we're curious about that. I says, well, I thought you were very keen to know if this batch that you have, this lot of materials, was actually going to last long enough. And he says, oh, yeah, but since we're doing this, we're going to, put more samples in there. And I go, well, we need, you need a whole lot more samples if you want to actually show that it's going to last this long. And it was a very simple design, but they just didn't get that. And so they tore apart all these samples. He sent me the data that one of the 2 samples that was in the chamber the whole time, so to speak, failed. And I said, well, it kind of indicates you may have up to a 50% failure rate here, just thinking off the top of my head. Yet it's really hard to conclude anything about your larger population because you kind of destroyed the sample that you were using. And I was like, oh, geez, what do we do with that? So a bad ALT in my mind is one that doesn't create useful information. It doesn't help you answer a question or learn about what's going on or articulate what's the time to failure distribution or something like that. You can spend a whole lot of money and get a whole lot of nothing. And I've seen in a couple different examples. What we really want are great ALTs. They are pivotal in making key decisions, and it might be selecting a vendor or it's a type of technology or evaluating a new technology or invention that you're doing. And it makes a pivotal difference in your business and profitability and all kinds of cool stuff. And it's timely, it's useful, it's understandable, and it gives you a model that you can use to simplify accelerated testing in the future as if you're looking to update or modify your whatever that is that you're working on or trying to extend its life and seeing if it works or not. Once you get a good test that gives you a really nice modeled understanding that particular failure mechanism, you got a base to stand on to make even further enhancements and improvements. Those, in my estimates, in my judgment, are great ALTs. They add value in and of themselves and create a platform of understanding that allows you to continue to make improvements or to assess conditions and so on related to that particular topic of that test. And I'm sure there's other types of ALTs that go out there. I'm going to add one more to the bad list. It's one that is just done because we always do it and nobody ever looks at it. Nobody uses the information to do anything. Well, that's a colossal waste of time. Let's see. Yeah, I got Carl. And see, I got a couple of comments here. Bill saying it can measure the extended degradation. Yeah, in some places. Yet in the example I was mentioning, Bill, they didn't have a way to detect any degradation in performance or material properties or anything on this thing. It was one of these components that probably had a pretty steep beta on a Weibull plot, and it had some defect or flaw that they were suspecting was in there, and they were looking for a very small probability of failure, yet was catastrophic for the products that this thing was in. Yeah, we explored doing degradation. They were taking these things apart just for fun, as all I could tell, is they had a screwdriver and they were going to use it. And you mentioned your book, which I'll come back to. We'll talk about that in a bit. ALT is a common tool in the reliability engineering toolkit, right? And I know universities teach classes, there's steps and programs and seminars and workshops and stuff and articles all over the place. There's books out there. There's a lot of information out there. Yet I find that just reading about it is not a great way to get really good at it. And so I'm going to go over a bit more about how do you actually get really good at setting up and conducting and analyzing accelerated tests. And I guess good is a relative term, yet to be useful, to add value. Now, some of you I know have heard this story or parts of this story. Early in my career, I was initially a manufacturing engineer, and then I moved into an R&D role for this company that made heating cables. These were devices that you'd plug in and it would heat. One of the products you might be familiar with if you live in a colder part of the world is called Frostex, and it's put in the gutter of a house or a building where there's snow and ice that could build up, and it heats it just enough so that it doesn't create an ice dam and it can damage your roof. And my grandfather's house had this happen all the time, and he would have icicles 20 feet long coming up off the upper part of the house, and just a big wall of ice, and it would damage the roof. So he'd have to go up and repair it every few years and so on. So this was a product to prevent that from happening. And it's used in all kinds of applications in industrial uses and so on. And my director came in one day and said, "Hey, you've taken a couple of statistics courses," and they were mostly like process control and control charts and hypothesis tests. Yet he considered me the statistician in the group, which was to his, to my chagrin, which I thought was kind of silly. And he said, "Well, we've got a customer that's interested in this new product we're making that they want to bury it in concrete in bridges in the mountains. And the idea is to put a little sensor next to the bridge that turns it on when ice would form on the bridge." And I know many of you have seen, the signs on long roads that saying icy conditions or bridges will be icy before other things and stuff like that. And there's all kinds of reasons why that occurs, right? Bridges are more exposed and they don't have the great heat sink of the earth underneath them and so on. And they said, "We're only going to buy this though if the product has a very high probability of lasting 20 years. Now you can understand that they didn't want to bury this stuff in the concrete as they built bridges, only to have to tear it all up and replace it, say 5 years later. And building a bridge in itself is expensive. And here they were thinking of this safety feature that would allow it to remain ice-free or minimize the amount of ice and snow that build up on bridges. And long story short is they ended up buying the product, and talking to people that live in northern Italy, they noticed that the bridges tend to be dry during even a big snowstorm. This product heats up just enough to melt off the ice and snow that accumulates so that the bridges stay relatively safe compared to being all covered in ice. And at that point, I had no idea what ALT was or accelerated testing, or that you could even do that. I had really no idea. The product testing that we had done was typically put it into a fixed chamber at a particular temperature, and we'd measure its performance after some amount of time, and it was sorted out and figured out years and years prior, and I wasn't involved in that kind of product testing at all. And so I really had no concept of, I knew that we tested products, yet I had really no idea what they were doing over there. I was really working on a variety of other things dealing with the manufacturing line and how do we make consistent product, and as opposed to ones that last in any period of time. And I looked at my director and says, "Well, I don't know how to do this. And he says, good, now you can go learn something. And said, go, you've got 6 months to sort out how to do it and get an answer. And I'm like, oh, okay, great. Thanks, boss. And so what I had been, and I still am to this day, is a book rat or a library rat. So the corporation had a really nice corporate library. And so I wandered over there and spent a whole day looking for books and papers and details on how do I cheat time. And the librarian said, oh, you mean accelerating something, accelerating a test. And I, okay, and I started looking up that, and I ran into Wayne Nelson's book, Accelerated Testing. And okay, I think I can follow this and sort this out a little bit, and started working on that. I ran into a American Statistical Association, ASA, newsletter. I figured, well, maybe it has something to do with statistics. Let me look in this thing. And they had a listing of conferences in the back of the book. And it just turned out that there was a life testing conference. And Bill, you might remember there was a journal that came out that was associated with this conference, and it ran for a number of years. And it was, I think it was called Life Testings, or LIDA, LIDA. I want to say that, but I may be confusing it with something else. And so I, noticed this conference coming up in the next week in Boston. So I went to that and actually met Wayne Nelson there and a handful of other people. It was a very small conference. I think there was only about 30 people there, and talked to a whole bunch of people about how do I go about doing this? What references should I look for? How do I approach this kind of thing? And got back home and said, I think I've got some ideas on how to handle this. As I need 3 different stress levels, and I need to create a relationship between the time to failure and the different stress levels. And then I could extrapolate that back to use conditions and go with that. I also learned that I really needed to understand, well, what was the failure mechanism? And so I started looking. I went, we're dealing with a polymer, and we knew that it oxidized. And as the oxidation of this polymer occurred, it was a process called chain scissioning, which is basically, think of a small knife or scalpel cutting the long strands of polymers into shorter strands, and that would change its behavior. It would expand and contract it with different properties as it heated and cooled in its normal use. And our product was dependent on that motion being consistent, because as it contracted, the product would enable the structure within the polymer, the material that we suspended within it, to become conductive. And so then it would generate heat. And as it heated up, it would expand a little bit, and then it would create less heat. So it was very temperature sensitive as to whether it created heat or not. It was pretty cool the way that worked. Yet talking to the chemists in the building, and it was a classic right out of the movies kind of chemical lab with all kinds of glass beakers and vials and bubbling things and strange smells and stuff like that. Learned about chain scissioning, and that was a chemical process related to how much oxygen was available and what temperature it was. And so he introduced me to the Arrhenius equation. He introduced that to me, not through a accelerated testing book or a reference or paper, but by a chemist saying, well, it's a chemical process, and here's this equation that deals with it. So later in Wayne's book, I ran across the reference to the Arrhenius equation as using it as an acceleration model. And so went back to and how important the activation energy was. And so back to the chemist. What in the world's an activation energy? And so he was able to, for the particular polymer and the blend that we're using, was able to run some experiments to in a chemist type way, which I didn't really ever understand, and said, well, this is what your activation energy value is. This is the value. I said, okay, well, I've got a model now, and I've got samples in 3 different stress levels running away. And it turned out that just learning as you go and asking questions and really starting with not even knowing what I was looking for, panned out within about 2 weeks to learning an amazing amount. When you start with nothing, then it doesn't take much to learn a lot. And was able to set up and run a test and get samples in chambers and start collecting data. And it turns out it wasn't that simple. It was probably one of the more difficult accelerated tests I've run into over the years. One of the assumptions, and this goes back to Wayne's book, is that he talks about as you set up these tests and make assumptions about the distributions or the behavior of it or its independence from one measurement to the next or sample to sample or a handful of other things that I would have never thought of. And it turned out that the samples in the chamber were not decaying in a linear fashion. They were slowing down in the rate of decay. And we could measure, ended up being a degradation test. And we're monitoring the rate of degradation of the ability of this unit to produce heat. And we had a threshold that we called a failure. And so an email and phone call with Wayne was like, well, yeah, these models really don't work for you. If it's that not linear in the way it's behaving, it makes extrapolating to when it fails pretty nebulous, because it's which straight line are you going to use? Because it's a curve, actually. And it's more along the lines of, well, you probably could model this curve and use that. And I had no idea how to do that. And one of the other people I met at that conference, and I've doing a senior moment here, drawn a complete blank on his name. He's a professor, and it was in Montreal. And I've drawn a blank on I think it was University of Waterloo. And I sent him an email and asked him, how do I model something that's not linear? And because I knew really basics of linear regression, and linear was a big part of it. If it's not linear, then that technique didn't work as well for what we're trying to do. So I spent a whole bunch of time with Box-Cox transformations and trying to force this curve into a straight line so I could use linear regression on it, and it just couldn't do it. So he suggested, well, why don't we use a Wiener diffusion process? I'm like, what? And so where you take a look at the differences between measurements and model the differences, and you can run out a regression in that fashion. I'm like, okay, so he did the heavy lifting for the modeling part and taught me how to do it. And we had the data and ended up writing a paper on it. I think that was his goal, the idea of having a good access to interesting data. At the end of the day, though, I had to explain this to the customer. And the paper wasn't published yet. That was still in the works. Yet here's this process, yet it was all grounded with the chemist standing next to me, explaining the chemical process that was actually going on, that was causing the change in the product over time. And a combination of that rate of change at normal conditions was actually pretty slow. And so I think that alone, even at the steepest rate of what we measured in the lab, would still last 20 years with a pretty reasonable probability of success. And yet, because the way the oxygen interacted with the polymers, it limited the amount of oxygen getting into the system, which caused the nonlinear behavior in the readings we were making. And that basically, it kept it safer. And it lasted even longer. So we were able to then quantify that they had some small probability of product failures at 20 years, and then a whole bunch of other information that went behind that. And they went upstairs and bought, I don't know how many millions of dollars worth of the product and started installing it. My boss never gave me a plaque or a promotion or anything for that. He ended up just asking me more questions about doing accelerated testing. And that started having that on my resume, or having that experience, and how much fun it was to do it, led to just one opportunity after another of continuing to learn. And I still am. I probably have a dozen different books on accelerated testing and reliability statistics and related stuff. I know I've read hundreds of papers. Somebody asked me a question years and years ago about temperature and humidity, and how does that accelerate something? And I says, well, it's in standards, it's in all kinds of places. And I asked a bunch of people and talked about it a bunch, and I found the couple of the original papers that kind of set that model in place, and where it was actually useful for, what that model was actually modeling. And come to the realization that a good number of applications of that formula, the PECS equation, PECKS, really didn't apply. Somebody was looking at adhesive properties. Yeah, temperature and humidity has an effect on it, yet the likelihood is the same as epoxy bonding to a frame for integrated circuit type component was pretty nebulous to me. And others, we were using it to see if the laminates on a solar panel would actually not cloud up and do this. And I was like, well, yeah, temperature and humidity might have something to do with it. It goes back to like the Arrhenius equation. If you really need to know the activation energy, and if you just guess, you'll get an answer, and it may or may not be useful. And it goes back to these technical papers are a great place that I found to, one, learn about different techniques and approaches. More importantly, though, is what stresses apply in a meaningful way, and sometimes even with a good model associated with it, for specific failure mechanisms. Corrosion is a chemical process in most cases, and it has a handful of models. Yet if you're using aluminum and you have a nice model with activation energies for steel, it probably doesn't apply. You would really need to check that out. Over the years, though, I've had, I don't know, countless numbers of discussions and email exchanges with all kinds of people all across, clients and friends and colleagues and peers and teachers and people I've taken seminars from and workshops with and so on, is a way just to continue to learn. And one of the things, it's like most of what we do in reliability engineering, is most of the stuff occurs is somebody invents a new kind of material just about every day, it seems like, or some mechanical engineer finds a new way to create a gearbox or something. We keep having to answer questions of, well, how long will this last? And while it may be similar to other things we see, it's just not the same. And so we continue to learn about materials and techniques and processes and failure mechanisms. So it keeps it pretty exciting. The reliability statistics part of it doesn't change dramatically fast. I still reach for the old books that have, how to create these models and how to set up sample sizes to optimize these models and so on. There's the, control charts, instead of X bar and R charts, we use X bar and S charts and for process control. And that's invented like 100 years ago, or really developed 100 years ago. I like that part, is that we have pretty consistent ways of approaching things. And in the advancing of computers allows us to do a much more sophisticated modeling, that's for sure. Yet the basic fundamentals of understand the failure mechanism and what stresses, how does the stress interact with that failure mechanism to make it happen faster in a meaningful way. Those basic principles are pretty solid. And I haven't stopped learning. There's no doubt about that. I'm constantly looking for more stuff to do. Yeah, and Bill's mentioning that modeling a reaction rate as a function of humidity is, yeah, I totally agree. When somebody asked me if they could add multiple accelerants to something, and is there a good model for that? And I says, we have a hard enough time with just one stress at a time. You put two stresses on it, they don't just add. if they interact with each other. And we know with humidity, the higher the temperature, the more moisture content can be held in the air. So 90 relative humidity holds a different amount of moisture depending on the temperature. So they're interrelated in a physics chemistry kind of way. And so separating those and creating a model for that gets complicated quick. Now add 2-3 more variables on that, and the interaction terms may or may not be important, yet it's really worth checking and understanding the nuances of that. And so instead of just 3 stress levels and trying to model that, you might end up with dozens of different points that you need to evaluate. So I know there's some progress in that. Physics of failures and the characterization of failure mechanisms is really making interesting models that can be used. Yet it takes a lot of work. I think that's why you have the room full of grad students working on developing these models in some cases. But anyway, there's still tons more to learn, and the ability to cheat time and get an answer has been a fascination of mine for, I think, close to 30 years now. And I'm still fascinated by it. There's no doubt about it. The number one takeaway I've had from my very first engagement with accelerated testing and with each one afterwards is, well, what's the mechanism? What is that physical, chemical, fundamental phenomena that's occurring? Are electrons going somewhere they're not supposed to go? Is silver diffusing to where it's not as effective anymore? Is this wearing down and in a manner that is either making it polished so it wears less, or is it making it rougher and makes it wear faster, or is it consistent? And it's 2 pieces of material, 2 metals rubbing against each other. And by very carefully understanding those surfaces and the rate of wear, gives you clues of how you can go about modeling it. How can you go about testing it? And if you just throw it in an oven and hope that it's going to accelerate something, well, it will. Is it something you're interested in? Well, maybe, maybe not. And so understanding how things fail and how they, at a very molecular level in many cases, go about not working anymore, just keeps me on my toes of the fascination of understanding the world around us and how things proceed to go off to create a failure. So accelerated testing is, in my mind, equivalent to understanding failure mechanisms. And it's hard to shake that with the experience I've had over the years. All right, so let's talk about some generic stuff here a little bit. How do you go about learning stuff? And this is based on, I had it up here a minute. It's I want to say Jennings is his last name, and he's come up with, how do adults learn type things. And he had 4 basic steps for it. And I'm paraphrasing and summarizing it dramatically, but it really rang true to me when I first ran across this some time ago. The idea is that it's really hard to learn anything unless you want to, unless you really try. And it was a pivotal moment when, I had my director standing there in my office saying, hey, we need you to go figure out how to do a test to figure out if this will last for 20 years. And I could have said, well, I don't know how to do that, and walked away, turned it down. Now, it would have probably been career limiting. And yet I think my boss knew that I liked challenges. I was the first to try new stuff, and we were constantly running experiments with what I was trying to learn and to do. And he was very, very supportive of, yeah, you need to learn this stuff. And one way to learn it is just try. And so we just tried, went to the library, went and did some research and so on. Yet I really wanted to figure this out. It was a challenge. I did not know a path to a solution. Yet I knew that it's been done. If it could be done, it's probably been done. And somebody's probably written about it. So I'm going to go find that. And the ability to walk into a library and then find a reference to a conference was serendipitous. I'm sure I'm not pronouncing that long word right. Fortuitous is probably a better word I can use and actually say. Yet there's a quote, and I was trying to figure out who said it. It was something along the lines of, if you think you can or you think you can't, you're right. I thought, well, I can go learn this. If it exists, I can find it and go learn it. And I wasn't afraid of what I didn't know yet, which is probably a good trait if you want to learn something. And I knew my first attempt was probably going to be pretty amateurish. There's no doubt about it. And I talked to my director about it a handful of times, and he was like, yeah, that's okay. We got nothing else. We got to give it the old college try, is the way he phrased it. So off to the library. I'm going to go learn this stuff. And you got to try. And if you don't try, well, then you haven't started trying to learn something. So this really is the first step. The next step is, well, let's practice. Can I measure something that actually is changing in a oven? We knew that we had a degradation in talking to the scientists in the company. How do I measure that? And so it was doing the homework with the chemists, figuring out an activation energy, doing the homework with the books and the conference materials and information I'd gathered in a couple of weeks, and really diving deep into that and asking a lot of questions and working out this samples and saying, can I Wayne has a handful of data sets in his book, and can I replicate his results with the tools I have, and working through those. And then I would run it past my director and a handful of other people in the building to say, does this make sense? Can I explain this to you? Does it hold water? Does this look consistent? Is this correct? And checking it against the books and the materials and papers I had, and lots of conversations just to check it. But yeah, sometimes you got to hit the books to learn something. Now, another step, and this is what I just naturally did, was I would go talk to people. Says, this is the way this thing fails. And everybody I, talked to were scientists and polymer scientists and chemists, and were, creating these products in the factory that we were doing, these extruding materials and all kinds of cool stuff. And there were a lot of very smart people at corporate that I could tap into. And as soon as I brought up, hey, we have this chain scissioning that occurs, and I'm trying to understand the rate that it does it and how it affects the product's performance over time. And I got way deeper into understanding that mechanism that I probably really needed to, because everybody wanted to talk about it. Everybody I brought it up to would set aside time to go just get into it and understand it, which was fascinating. And then I would bring up, well, how do I model this? If it's a nonlinear regression analysis. And then usually people's eyes would roll back in their head and says, all right, we're done now. I got to go to lunch or do something else. So then I relied on folks like Bill Meeker and Wayne Nelson and a handful of others that I met at that conference, and a handful of others I eventually met at professional meetings and so on, to Well, and I was also taking a bunch of courses for my master's in statistics. So I was bringing the real world problem into class and going, how do I deal with this? And so picking their brains about approaches and how to do stuff, and how do I check if something is a normal distribution or not? Right. I never knew how to do that. So learned how to do it and found people to talk it through. But it's a critical step in learning something, is you need to jostle around in your mind, either trying to explain it to somebody else or asking questions and attaching that onto your own experiences and backgrounds. They may ask questions that reveals or provide comments or insights that allow you to see that topic in a different way, and so on. I found that the conversations really cemented that. One, gave me confidence I was on the right track or it was way off, but it allowed me to get a deeper understanding of what I was learning. And then where I was working, I had about an hour commute. And so that led to plenty of time to reflect, just to think about it. I was also using a technique called morning pages. It's like journaling. So first thing in the morning, write 3 pages longhand. And it was a way for me to just randomly think about the stuff I'm working on and how it fits together, and what questions do I still have outstanding, and what are the next steps, and how do I analyze this, and how do I explain this? And it helped me to really remember the lessons I learned. And this process of learning ALT includes, you got to try, right? Practice and study and experiment, get a safe way you can try things, work the examples is my favorite process of doing it. And then talk to people about it, discuss it. What's the hard part? What's the easy part? What's the areas you're not sure about? What are your thoughts of this? How would you approach it? And so on. Just talk about it, and then spend time to think about it, just to reflect what's working or what's not working. And that comes from Jennings, is 4 steps on how adults learn. And so I'm talking about it in context of accelerated testing, yet I find that process is a great way to approach just about anything that you need to learn, especially if it's related to work, because you generally have other people that you can talk about it with, and which is a key piece to it. I'm not sure how big that truck is coming up the hill, so hopefully it's not too much of a noise for you. Let's see. We got a handful of comments and statements here. Let's see. Carl's adding some notes. Bill's adding some comments and notes. Let's see. Accelerated presentation slides, basics of accelerated. Great. 5-reason cobots. I'm not sure what that is. Will never be completely safe. Interesting. Principles of failure hard. Good. Couple definitions. Accelerated validation testing, accelerated stress testing. That's probably a whole nother webinar alone on that one. There's places that, in my mind, it really depends on what you're trying to do. And I'm talking about the validation testing or stress testing. And it gets, I don't know, I probably do a whole webinar, like the 5 questions I would ask when I get a question like that is, what are you trying to achieve? What do you already know? How important is it? All those kinds of things, is get a context for that. So let me get back to the learning piece. One of the things, and a couple years ago, there was this phrase rolling around that if you wanted to become an expert at something, you just needed to do it for 10,000 hours. Well, that wasn't quite the right quote or takeaway from that body of work. It was get deliberate practice. if you have to deliberately practice playing the piano for 10,000 hours or whatever the time frame is, but it's not insignificant time, with somebody coaching you, with somebody guiding you, with somebody providing more insights of what to do. So to learn accelerated testing, it's the book gives you a basis to start, right? The discussions is getting you the feedback. Even better if you can find a coach or a mentor or a professor that you're taking a class from, or a workshop or seminar from, and get feedback. How did you do on the problem set? How did you approach the problem in an appropriate way? And did you check the assumptions? How did you verify that, yeah, these things are really independent, or they are not independent? Is it a linear degradation, or did it drift off into something that linear regression is not useful for anymore? How did you verify all those things, or check all those things, I should say? And yeah, some people can get through all of those skills and master them on their own. Yet I found with accelerated testing is getting the feedback, getting input on, is this working or not working? Is it understandable or not understandable? Was essential in order to get this test done and the results in a form that was meaningful, that enabled that client to go, yep, we got it. We understand. That makes sense. We understand it. We understand that there's still a risk. We'll buy it. And but without the feedback, I probably could have engineered a test and sorted it out. It might have taken me years. Yet getting feedback that I was in even the right chapter of the book was, time saving to no end, and really accelerated my ability to learn this stuff. So whatever you're learning, is get a coach, get somebody you can bounce this stuff off of, and they can see what you can't see, whether it's learning how to be a better presenter or doing an data analysis, is get some feedback. Get somebody that's going to be your editor or coach to do it. All right. So let's talk a little bit about some resources. I mentioned Wayne's book, and I actually wore out my first copy of it, so I had to track down another copy of it. Bill's book, I've had his first edition for years and years and years, and have enjoyed it. And it's more than just accelerated testing. It's got all kinds of stuff in it. And Bill, I couldn't find, there was a ASQ pamphlet, for the lack of a better word. It wasn't full book form, but it was basically optimizing sample sizes for when you had 3 different stress levels. And I think what I took away from that, I think it was you, Bill Meeker, Willie Meeker, and Hahn, H-A-H-N, I believe. And I'm drawing a blank on his first name. It had tables and charts and formulas and all kinds of cool stuff in it. And there was a way to optimize it. It was a bit too complicated for me to sort out and make work. Yet my takeaway was a 4-2-1. It was a 4-2-1 approach, where you put 4 times the samples in the lowest stress that's closest to your normal use conditions, and in a ratio, and then 2 samples in the middle stress and 1 sample in the highest stress. And there was rationale for that and all the other stuff. It wasn't quite optimal, but it was close enough, and I found it to be very useful over time. So those are the 2 books. And Bill's book, the second edition of Statistical Methods for Reliability Data, which I think on the spine is SMRD 2. I can see it over there. Updates a good amount of the material in there, and has lots of cool stuff in it. So it's one of the 2 books I recommend highly when you're getting into reliability statistics or accelerated data. The other key piece, and it goes back to my very first step when I was learning this stuff, was I go to the library. All right. if you are an alum and have library access, it's great. Many companies have a library or have library access to some facility or group or whatever. Google Scholar is a great start, yet a lot of papers are behind paywalls or stuff like that, which is unfortunate. Sometimes you can track down an author and get a paper directly from somebody. Places like ResearchGate have used that way and have shared papers I've published that way. Yet the technical papers they might not be titled a accelerated reliability test for XYZ or some technology or material. It may be a paper about that particular material, that type of steel or that new alloy that's coming out. And one of the ways materials and technologies are evaluated is for their durability, for their lifetime. And so not all, but many papers will then have outline of how they evaluated, what kinds of stresses did they apply and how did they model it. And some papers are meant to be a paper about the accelerated model that they developed or used. Those are gold if they really apply to your particular application, to your particular failure mechanism. Go look for things, how things fail is a great way to understand how things work. And so technical papers you have to do a bit of digging, and preferably if you have a really skilled technical librarian on your side, you can find a lot of things available that will really shortcut your time of having to design and build an accelerated test. If you started from scratch every single time and had to create your own models every time, it gets expensive and pretty costly to do, I should really say. So stand on the technology or the information that's been shared in our technical literature and build on that. It really helps you make advances much quicker. And there's plenty of papers and technical articles and all kinds of different material out there on just what are the different accelerated life testing methods. And we mentioned this degradation testing earlier. I always joke that it's kind of like close to the last chapter in Wayne's book. He talked about all kinds of other forms of accelerated testing. And I took the one that was in chapter 14, I think, as a starting point. I often cringe when I think about, if you're starting off at the advanced level in a technical topic, that you're jumping in the deep end of the pool, so to speak. And it worked out. I had plenty of support. There's all kinds of ways to do accelerated testing, and some are, making more assumptions than others. And so selecting the approach that you're using often depends on your particular circumstances and what you know and don't know. So having a good awareness of the techniques that are available is a good setup in your toolkit of how do you go about designing and running these tests and analyzing them. And then there's websites and conferences. I have to mention Accendo Reliability, of course. There's, dozens and dozens of articles and small tutorials and case studies and stuff like that on accelerated testing. There's all kinds of stuff. If you don't find what you're looking for there, let me know. I probably know if it exists or not, or I know a handful of authors that could probably help you answer your questions or even write the article on it or conduct a podcast on it. Weibull.com is kind of an encyclopedic deal on reliability statistics, and they do include accelerated testing, more so with their software, Alta. So if you go into their manuals and books and articles and papers and stuff that we deal with the Alta software, there's quite a bit there and very informative. The Engineering Statistics Handbook is published by the National Institute of Standards and Technology, if I got what NIST stands for correct. And it continues to evolve, and they add all kinds of techniques and skills and statistical stuff. It's not just accelerated testing. It goes way beyond that. And they do have some handful of informative pieces on it. Conferences, I know, and I've been associated over the years and with the RAMS conference. And I should also mention the American Statistical Association. I did run into a handful of small conferences that were specific on accelerated testing. So there's plenty out there if you look for it. And your mileage may vary, depends on who's presenting and how versed they are at presenting, yet you can probably find people to talk to about accelerated testing at these conferences. And then there's hundreds and hundreds of specialized ones. If you're interested only in wind farms and the great big gearboxes that go on these wind power generators, or just the inverters that convert the energy from DC to AC and put it up on the grid, there's workshops and seminars and conferences occurring, often industry specific, yet are wrestling with reliability issues or topics, and sometimes accelerated testing for these things. So there's no lack of where you can go find people of the birds of a feather, so to speak, to go learn from and talk to folks that are writing about accelerated testing in one form or another. Let's see, I think I saw a couple notes come through. Jerry hand, thanks, Bill. Yeah, 1985. That was shortly before I actually had to go design a test. So it was, hopefully it was pretty in time, in date at that time. I really hope so. Yeah. And there's lots of cool, one of the trouble pieces I have a hard time with, Bill, on computer tools to set up a test is that if you don't really understand what it's doing and what the trade-offs and assumptions that you're making, and if they're valid or not, you can get a really nice plan for exactly the wrong problem, or the wrong plan for the right problem, I should say. The idea is that we got some great tools, yet you really still need to know what you're doing. And I ran into that with linear regression. There's simple basic stuff. I run colleagues that they refuse to plot the data on the regression analysis or in their plots of the data or the plot of the regression because it didn't match. It was very, very far off. It was obviously a great big curve and they were putting a straight line through it. And sometimes that may be perfectly useful, and sometimes it was absolutely wrong. And it's like, do the plot with the data. Let's check this. It's just a simple check. There's other checks to do. Regression analysis has a handful of other ways to go about doing it. Yet if we just assume, and I run into this in reliability all the time, well, we assume it's in the flat part of the curve, so everything's exponential, so we can just add the failure rates. Well, let's think about this. What are you really trying to understand or model or calculate here? So if I use a computer tool, I almost always have to run known examples through it. I need to understand, play with it this way and that, and where its limits is the problem I'm trying to solve suitable to be answered by this particular tool. I guess I'm just a little bit skeptical, even of my own work, is check and double check. And I don't know if that's a good thing or not. Last step is go take a course. There's university courses, there's online courses, there's workshops and seminars and all kinds of stuff that's out there. I know Stephen Wax offers a course. It's based on Minitab. I know Bill Meeker has done workshops and seminars and stuff. And I don't know if your material that was done with JMP is still available. That was good stuff. The course itself helps you learn the language and the basic steps and all those other nuances and considerations. Yet I think it also encourages you to ask questions, to interact, to get online, to send an email, to get on the phone, take advantage of office hours, those kinds of things. That third step in how we learn is the discussion part. And so don't miss that part. I think it's very important. And then there's coaches and mentors, and they can be in your company. They could be in a different discipline, like that chemist that I worked with wasn't really a statistician, yet we were able to, he was able to fill in the blanks for me and encourage me to learn the statistics part. He saw the value in it, and so helped me kept going with that. Same with my director at that time. It was like, no, we know it's an experiment. Let's try it and let's talk about it and let's figure out which one's working for us and go with that. So he was really a coach, saying, you know, of all the stuff you just mentioned of what you're reading about and doing, let's ask some questions about it. Let's talk about it. How about this, this, and this, and maybe find some more on that. It was those steps that really got me started with accelerated testing. And it was those bits of encouragement, bits of getting pointed in the right direction, and just giving it a try. And then what I found is that as I kept learning about this stuff, and it turned out that people said, oh, well, you're the one that does the accelerated testing. And so years later, I'm at a different company, and I'm working in manufacturing as a manufacturing engineer mostly. And somebody said, you know how we're going to consider this newfangled component, it's an electronics component, and we don't really know if it'll work in our application for the duration that we want it to. And it was 5 years is what they were looking for. And I said, well, I know how to do accelerated testing. I've done that before. And so I got charged with sorting out, is this new technology going to work in our application? Will this circuit or integrated circuit component, a new way of doing the solder joint attachment, it was going from gull wing to a gull wing lead to a ball grid array. And then it was a pivotal change in how much the product cost and how well it worked and all the other stuff. And it took about 6 months to run the test and create convincing information. I learned how to use an X-ray machine, a bunch of other stuff I got to learn how to do. It was a very straightforward accelerated test with a couple, and we had good models for the solder joint fatigue and so on, and ended up saving, being a pivotal piece of information for the company to use this new technology and all of its advantages. And I wish at the time that I had figured out, well, just how valuable it was. It ended up being a part of a $500 million industry. It was in all the products that were going out. So it's a journey, and it's still going on, and I'm having fun. So hopefully you get to enjoy it as you explore doing accelerated testing or whatever it is you're learning. I think the ideas and concepts that I outlined here in the story I told hopefully helps you to, continue to learn as you go on and master all the stuff we do as reliability professionals. So I'm going to have to run. I'm already a moment late, already texted him saying I'll be there in a moment. So I got to run to another meeting. If you've got questions or comments, send them on over. I'm looking for questions on accelerated testing so we can do another Q&A session on that. I thought that was a lot of fun, and I'll try to pace it a little better so we don't run out of time and rush through them too much. But we'll be there in no time. I think in the next month or two, we'll do something like that. So if you got questions, fire them off. I'll leave the chat window here open for a few minutes, but I'm going to go mute and turn off the recording as we go. So thanks so much for attending today. I really appreciate it.